This video is an introduction to logarithms. If you missed class or the warm-up, you should pause the video now and come back when you've completed it. Take a look at the answers to the warm-up here. You'll notice that the blue is the function g of x, and I've just estimated some of the points here. It's a little hard to draw. The inverse function, of course, is the reflection over the line y equals x. The original function is an exponential function. And to get these answers, you can use Desmos or just plug in the x values, 1/2 to the power of -3. Use your calculator, it'll give you 8, and so on. I asked you to look at the asymptotes, domain, and range for the function and its inverse. And if you remember, exponential functions all have an asymptote. So in the case of the original, our asymptote is the horizontal line y equals 0. Well, because this is a reflection over the line y equals x, the inverse is, the new asymptote is the line x equals 0 for the red, the inverse function. And if you recall, the domain and range just change for a function and its inverse. So before the original function, the domain is all reals and the range is everything greater than 0 for y. Because of the asymptote there, it's only up from the 0 value, not including 0. And for the inverse, those things just switch positions. But of course, since we're talking about domain now, we can't use y, we have to use x. The third question asks whether the functions are increasing, growth functions, or decreasing, also called decay functions. When you're asked about whether something is growth or decay, or increasing or decreasing, you read the graph from left to right and ask yourself what's happening. So if you're walking the graph, what's happening? Is it going down or is it going up? What's happening to y as x increases? So this is really an end behavior question. Both of these functions are decay functions because as x increases, the value of y decreases. Now in the case of the blue, it never goes below 0. It doesn't actually even touch 0, but it is a decay function. It is always going down, just not very quickly. So here's the reason that we started with inverse functions, particularly with exponential functions, because logarithms are just the inverse of an exponential function. So this blue function is sort of the parent exponential function, y equals 2 to the power of x. And when we graph the inverse function, the new notation here is y equals log base 2 of x. So the notation is on the right here. If your function, f of x, is 2 to the power of x, then the inverse function of f inverse of x, is called the inverse function, and it's equal to log base 2 of x. Notice how I read that, log base 2. Isn't this 2 also the base? 2 is the base, x is the exponent, and so we read it the same way. So again, if you haven't done this in class with me, I'd like you to spend 5 or 10 minutes doing some research on the meaning and application of logarithms. There's lots of them. We're going to discuss them together, and if you're doing this completely by video, I will show you a screen with some of the observations that other students have made. Make sure to use your own words here. You can scan this QR code, which is a good site I found. You can search on your own using Google or some other search engine. Mathisfun.com is a little more basic, but it's also a good place. You're to read for understanding. So if you go to one site and you sort of don't get it, try to find another site. After the time is up, 5 or 10 minutes, you should go read today's Schoology discussion, and I've put instructions for you to complete that. I should see lots more in the Schoology discussion from you, but here are some observations made in a class I had last semester. Erin saw that negative logs are division, and Sydney saw that logs are used in senses. Clay found the conversion from an exponential function to a logarithmic function, which is something that you'll learn how to do today. Also, logs form spirals of a seashell, so they appear in nature. Logs answer questions about the exponent. That's a nice way of telling us where the answer to a log function, what it's telling us. You can see the x here is the exponent in exponential form. And there are some other observations here that you should read through and see if you found some of these same things. The natural logarithm has a base of e, which is a special number called Euler's number. That's the way you say that, Euler, not Euler. And the notation for the natural logarithm is ln. We will learn about that as well. Binary code is base 2 logs. Logs is just short for logarithms. And there are some other things here. So it's important for you to know and write in your notes the conversion between logarithmic form and exponential form. When you write these down, and I've boxed them in red, keep in mind that the letters could be any letters. It's the position that's important. So often you'll see these with different letters in different places. The biggest thing is that the base here is still the base here. And the answer here in logarithmic form is the exponent here in exponential form. The if and only if, this just means that this is true forwards and backwards, which is important. If and only if means that a statement is true forwards and backwards. And so this is the way you'll see a logarithmic function, and you're going to practice switching between forms. F of x equals log base b of x is a logarithmic function with base b. So logarithms really are exponents. Let's take a look at some examples. We're going to convert these to logarithmic form. So let's see how we do it. Remember, the base is still the base. So if this is going to log form, I'm going to do log base 3. And the answer here, the answer to this one is going to be the exponent here. And so that's our x. That means this 9 has to go here. And if you look back at this problem, it's actually easier to solve in exponential form. So usually we're going to be asked to convert between forms just to help us solve the problem. In this case, it's not really easier to solve in logarithmic form because the numbers are easy. We know that 3 squared is 9, so x must be 2. But these numbers aren't always so easy, and you're going to learn a way to put this in your calculator. So if x is in the exponent, logarithmic form gives us a way to get it out of the exponent, so we can use our calculator to solve it. Let's practice when you can't actually solve the problem. In this case, x is 2, which we really found here. We're doing log base 5 because the base is still the base. And the answer to the log problem is the exponent. So that's where the x goes. And then this position must be the y. And so you the base is the base. The answer to the log problem is the exponent from exponential form. And whatever's left is what you're taking log base 5 of. In this case, just y. Let's look at going the other direction. log base 2 of x equals 4. So the base is still going to be the base. Now the answer is the exponent. So that goes there. That means this must be equal to x. 2 to the power of 4 equals x. Well, 2 to the power of 4, you either know it or you can do it in your calculator. I know that x is 16. And so that's a convenient way to solve this, where in this form, we really don't know what x is equal to. There's no way to put this in your calculator. The idea really is to get the x by itself on one side of the equal sign. So whichever form will help you to do that will help you solve the equation. And then, of course, there's times when it's just a function, x and y. You can't solve it if there's two variables, but you can switch forms between logarithmic and exponential, and there will be times you'll need one or the other. So if we're changing this to exponential, the base is still the base. The answer here is the exponent. That's a y in the exponent. This looks funny. This is 4 to the power of y, and it must be equal to x, because that's the only thing left to use here. So 4 to the power of y equals x. We're going to practice more of those in class together. So I know this is a very brief overview to logarithms, and we'll do more together. In summary, we've learned what logarithms are basically. They are inverse functions of exponential functions. We know why we use logarithms. Briefly, we can convert between logarithmic and exponential form to help us to solve equations. How we do that is when we're converting, the base stays the base, and the answer to the log problem is the exponent in exponential form. We'll be practicing this more in class together.